going to do a new unit. This will be the unit that covers through the end of the year. We're going to cover probability and statistics. Within probability, we're going to do what are called counting principles. This is what we'll be doing today. Then we'll also do single and multi-event probability. And within statistics, we're going to analyze data using mean, median, mode, standard deviation, normal distributions, things like that. And we're also going to talk about how we collect data efficiently and effectively. As I said, today we're just going to talk about counting principles. Before we do that, I'm asking you to introduce probability, just defining it. So probability. Probability is the likelihood of an event occurring. I'll give some simple examples of that. Some of them I'm sure you're familiar with. Let's say we want to talk about the weather, and you say there's a 30% chance of snow tomorrow. So what does that mean? That is the probability, the likelihood of it snowing tomorrow, 30% chance, which is on an average. On average, if we had 100 days like tomorrow, 30 of those, 30 out of 100, or 30%, it would snow. Let me give another example. Let's say you flip a coin. What is the probability of getting a tail on that coin? That I think most people know is 50%. Or 1/2. That is the probability or likelihood of that event occurring. So where is this used? It's used a lot more than just flipping coins and predicting weather. It's used in almost every aspect of the economy and life, I would say. So one example is financial markets, or finance generally. For example, the value of a company. Apple, the company, is worth about $1 trillion today. If that's assuming a certain level of success, a probability of their next phone, for example, being successful, and the one after that being successful, that entire value is in fact based on the probability of things happening to it in the future. Let me give another example. Insurance, like car insurance rates. Car insurance rates for people are entirely based on the probability or likelihood of them getting in an accident in a car. And companies use your age, your driving history, your gender, all kinds of things like that in order to determine that. So there's one example, again, where probability is heavily used. Another example, medicine. Doctors use the likelihood of a treatment working versus another treatment in order to determine what to actually recommend. Insurance companies, again within medicine, not only use the likelihood of something working, but also the cost of that treatment, and they balance that off. Let me give you another example. Games. Things like card games, poker, blackjack, dice games, things like craps. People know what that is. Those are entirely based on probability. And I think if you think through any fields or many fields around that anything you can think of, there's some inherent probability based in them. So this stuff is hugely useful. Okay, so how do you calculate probability? So probability is calculated by dividing the desired outcome, what you are trying to figure out is going to happen, versus the total number of outcomes. So I'll give some examples of the same ones I gave before. For the weather, the probability of snow, for example, was simply on 100 total number of outcomes, 100 days, it's going to snow 30 of them in a day like tomorrow. And therefore the probability is 30 over 100, or 30%. Let's take the probability of tails on a coin flip. Total number of outcomes, you have heads or tails. There's 2 outcomes. How can you get the desired outcome? Tail, just one way. So the probability is 1 over 2. Okay, that's how you calculate it. Now what we're going to spend today doing is actually just focus on the denominator, the total number of outcomes. When we do probability, we also talk about the numerator, but today we're just going to talk about the total number of outcomes. The way you calculate the total number of outcomes is by using what's called the fundamental counting principle. The fundamental counting principle is basically just a way to determine how many different ways something can occur. And the way you do it is if you've got a couple different events that you're talking about, say one event I'll call M, which has M different ways of occurring. And you have another event, we'll call it N, has N different ways of occurring. The fundamental counting principle basically says that if you want the probability of, or the number of outcomes rather, number of total outcomes of two things occurring, or three things, all you do is you multiply the numbers of each of them together. So let me give some examples of this to make this a little more transparent. Let's do the coin flip again. Except this time I'm going to flip 2 coins. I want to know what is the total number of outcomes. In other words, the denominator of probability. So you have 2 coins. The first coin, you can get a head or a tail. The second coin, you can also get a head or a tail if you flip 2. It doesn't matter if you flip them in order, one and then the other one, or at the same time. Same possibilities. So what is the total number of outcomes rather of 2 coins flipped? It's 2 times 2, or 4 total outcomes. And this is small enough for that I'm just going to write them all out. You get a head the first time and a head the second time. You get a head the first time and a tail the second time. You get a tail the first time and a head the second time, or you get a tail the first time and a tail the second time. Those are my 4 total outcomes. So now I could use this. How do we use this? We use this for probability. I could say, what is the probability of getting 2 heads, a head and a head again? The answer is, my denominator is 4 total outcomes. My numerator is the ways I can get 2 heads, which is just one way, 1/4. Now, what are the odds that I get, so this is just 2 heads. What are the chances that I will get at least 1 tail between these 3 rows? The answer is 1 there, 1 there, 1 there. That's 3. Total outcomes, 4 or 3/4 chance that if I flip 2 coins, I'm at least going to get 1 tail out of that. All right, so let me give you another example. This time we're going to flip 3 coins. So first coin is 2, second coin is 2, and third coin is also 2. So now total number of possibilities, 8. This again is small enough I can write all 8 out. I can get 3 heads. I get a head, a tail, and a head, add a head and a tail, or a head, a tail, and a tail. Or I can start with a tail, get tail, 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 head, tail, 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 head, or tail, head, head. There's my 8 outcomes. And now I could use those, again, that's my denominator. I could use that for any sort of probabilities. Like, for example, I want to say, what are the odds that I'm going to get at least 1 tail out of there? These all have 1 tail. The only one that doesn't is that one. So it's a 7/8 probability that I'm just going to get I'm going to get at least 1 tail. If I want to know, say, for example, what is the probability that I'm going to get at least 2 tails? 2 tails. Denominator is still 8. That's why I calculated it. And 2 tails is 1 there, 2, 3, 4. 4 different ways. 50-50 shot. 50% shot that I will get at least 2 tails out of 3 coin flips. Okay, let me give you another example. This time I'm not going to be coins. We're going to use license plates, and specifically Colorado license plates. So a Colorado license plate is made up of 3 letters. So I'll call it A, B, and C, and 3 numbers. 1, 2, 4, say. The question is how many different license plates can you create? In other words, what is the total number of outcomes? Well, for the letters, there are 26 letters. So each of these has 26. And the numbers, there's 0 through 9, so each of these has 10. So how many total license plates can you create? 26 times 26 times 26 times 10 times 10 times 10, which is 17,576,000, which is plenty. We only have about 5.5 million people in Colorado. Unless everyone has 3 vehicles each, including infants, that's going to be plenty forever, basically. You'll also see, like in California, for example, where you have 35 million people or so. That's not enough. So what do? They have 7 numbers on their license plates. They don't have 6. So they just put a number up in the front, like 2. This can now have 10, And this number just gets a 0 out of it. And now you can make 175 million license plates, which is enough for California. Okay, that's a couple examples. Let me give you one more example. Food ordering. Let's make a pizza. Let's say you had a pizza and you had some choices. You had choices of crust. You can make wheat or white. You have choices of meat. Sauce first. Red, white, none. You have choices of meats. Say pepperoni, sausage, Canadian bacon. Let's get another one, hamburger. And you have choices of vegetables. Let's say we get mushrooms, not really a vegetable, fungus, but we'll put it in mushrooms. Peppers, tomatoes, and let's get a fourth one, potatoes. Okay, so how many total different types of pizza can you create, if assuming you use one for each area? Well, you have wheat or white, there's 2 possibilities. Red, white, or none sauce, that's 3. Pepperoni sausage, Canadian bacon or hamburger, that's 4. Mushroom, peppers, tomato, or potato, that's another 4. So what is the total number of pizzas you can create? 2 times 3, 6, times 4, times 4, or 6 times 16, I think that's 96 total pizzas. There we go. All right, that's the fundamental counting principle. Notice one thing about this, and this will come up what I'm about to do here. I allowed repetition, and that'll be important in a second. Let's see, I'll put that up here. Allow repetition. So, for example, when I have the license plate, this was a perfectly legit license plate. AAA 000, or BAB125. In other words, I was allowed to use B twice, or in this case, A 3 times. That's a lot of times that is the case, but I'll talk about some examples now where that's not allowed, where you're not allowed to have repetition. First one I'm going to give you is an example of hang clothes in your closet. Let's say you have 5 shirts and 5 hanger locations in your closet. The question is, how many different ways can you hang those 5 shirts? Again, you're still looking for outcomes. Now, so let's say you hang the first shirt up on the hanger. There's 5 different places you can put it. So this gives me 5 total outcomes for just the first shirt. Second shirt, however, I can't hang it in 5 different places because one of them's actually already, I already used the shirt. I can't hang it again. So actually, I've only got now 4 shirts and 4 locations. So where can I put that? And the next one is, I have 4 different places I can put it. Now I've hung something in the first slot and the second slot. I've only got 3 slots left, and I have 3 shirts left. How many different places can I put one of those 3 shirts? The answer is 3. Then the next one is 2, and then finally 1. So that was because repetition wasn't allowed. I wasn't allowed to hang the first shirt, the one shirt up in the 5th in one position, then put it in another one, then put it in another one, and then put another one. I couldn't put the same shirt in 4 different locations because I used it already. Notice this. This is called a permutation. I'm going to write that up at the top here. And the first thing I'll say is repetition is not allowed. So let me give you another example of repetition not allowed. You are playing the lottery. And you have 5 numbers to pick. And they can be between, say, 0 and, let's take a 0. I don't think you usually can get a 0 in a lottery. Let's say 1 and 52. So which is 52 total numbers. So if you were allowed to have a lottery number, which was, say, 2, 2, 2, 2, 2, then the number of outcomes, possible outcomes here, would simply be 52 times 52 times 52 times 52 times 52. But you're not. This is not an allowable lottery number. You can't repeat the numbers. They pick them out with a ping pong ball. Once the ball's out, you don't get another one. So that's not an allowable lottery number. However, you can think, again, I have 5 digits, 1, 2, 3, 4, 5. The first slot, I do have 52 possibilities. Any numbers 1 through 52 can work there. The second one, I've used up my number. I only have 51 numbers left. So it could be 51. The third one, 50. The second one, 49, and the final one, 48. So what is the total number of outcomes? 52 times 51 times 50 times 49 times 48. That's not quite correct, because actually in lottery numbers, the order, in fact, doesn't matter. How you pull the ping pong balls out doesn't affect it. In other words, the lottery number 1, 2, 3, 4, 5 is the same as the lottery number 4, 4, 3, 2, 1. So this isn't quite correct. But you can see you do have to drop. I'll get to this, the other point in a moment. You have to drop 52, 51, 50, 49, 48. This idea is called a permutation. And you may have noticed this last thing we did, I think, in sequences, we also had something that did like this. It was called a factorial, where you started with a number and you multiplied by numbers lower than it by 1. So you calculate permutations with a factorial. Okay, one last thing I'll put up here, and we'll talk about it a little bit later, which is indirect permutation is not allowed. This is also order is important. In other words, in that example I gave you of the lottery number, if you're going to do a permutation, this is a different lottery number than that. Now, reality, lotteries don't follow permutations. They follow, we'll do in a moment, which is called combinations. But if these are two different things, then this is a permutation. Okay, so let me go through some factorial things just as a reminder, and we'll do a couple more examples. So factorials is what we're going to use to calculate permutations. Here's the definition of a factorial. It's, say, 10 factorial is the first number times 1 less than that, times 1 less than that, and you keep going until you get to 1. So, for example, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Then you multiply it out. 6 times 5 times 4 times 3 times 2 times 1. And you get, oops, that didn't work. Do that again. 720. Okay, I'm gonna have you do a couple in just a second. Let's do 5 factorial and 3 factorial. Okay, pause the video here and do these two calculations. Okay, 5 factorial is 5 times 4 times 3 times 2 times 1. 20, that's 120. 3 factorial is just 3 times 2 times 1, or 6. Okay, so now I'm going to give you the permutation formula. You're not always taking these things one at a time. Let me give you an example of that first. So let's say you have 10 people racing. So we're doing permutation examples. And then I'll give you the formula. If you have 10 people racing, and you want to know how many different ways they can finish first, second, or third. So I only have 3 positions. So when in the first position, who can finish first, there are 10 different people who can finish it. Second one, that person's already finished first, they can't also finish second. So that's 9. And then the third one, there's 8. So the number of total outcomes of 10 people racing and wondering who finishes first, second, or third is 10 times 9 times 8, which is 720 different ways. Notice that doesn't go all the way down to 1. So that gets me to the permutation formula. The way you actually calculate permutations, first we write with a big P for permutation, is written as n things, like 10 people, and you want to know how many in order, or grouping of 3, which I'm going to call R, is simply n factorial over n minus R factorial. So pause the video and write that down. That's the permutation formula. And I'm going to show you how, okay, pause it. Okay, now I'm going to show you how it works with this. In this case, I'm doing the permutation of 10 things, 10 people racing, and I want to know who finishes first, second, or third. And therefore, this should give me this 720. So n is 10, n minus r is 7, like that. It's 10 factorial, 7 factorial. And you remember this from last section as well. I can now write 10 factorial is 10 times 9 times 8 times 7 factorial, divided by 7 factorial. Those cancel, and there it is, 10 times 9 times 8, or 720. Okay, now I can just modify this slightly, and let's say I cared how many, I also wanted to know how many people could finish first, second, third, or fourth. The only difference would be, it would now be the permutation of 10 tens taken 4 at a time, or 10 factorial over 6 factorial, which is 10 times 9 times 8 times 7 times 6 factorial over 6 factorial. Those cancel. And now I've got, to multiply that out, 10 times 9 times 8 times 7 is 5,040 different outcomes total. Okay, I'm going to give you a couple permutation calculations to do for examples, just numerically. Let's take the permutation of 7 things, taken 2 at a time. Why don't you pause the video there and do that? Okay, if you're back, that is simply 7 factorial over 7 minus 2 factorial, which is 5 factorial. Start distributing that out like that. 5 factorials cancel, and you get 42 different outcomes. Let's try another one. Permutation of 100 things, 98 taken at a time. Pause the video there and calculate that. Okay, this is 100 factorial over 98, 100 minus 98, 2 factorial, which is an enormous number. 100 times 99 times 98, etc. Divided by 2. Now that's a ridiculous number to calculate. However, you can do that in your calculator. If you go to the probability, if you got a TI, you've got a probability function. It's under math prob. Hopefully you remember this from last time because it had factorial in it. You'll also see it as NPR. So I can calculate this. However, mathematically that's a real pain. It's a huge, huge number. Okay, let me give you an application of this. It's also the application in your notes or in your presentation sheets. So I've got a disc jockey who can play 7 songs in a playlist. And the order is important. In other words, I could play the same songs. I could play them in 1, 2, 3, 4, 5, 6, 7, or I could play them 7, 6, 5, 4, 3, 2, 1, and that is a different playlist. So 7 songs, and I have 13 to choose from. And the question is, how many different playlists can I create? Okay, the answer to this is, it's a permutation of 13 things taken 7 at a time. So it's 13 factorial over 6 factorial. So this one I'm going to do in my calculator just to show you how to do this. If you have a TI, if you don't, it's probably there someplace if it's a reasonably complicated scientific calculator. So I'm going to do 13 factorial over 6 factorial. I'm going to do that first by just using the factorial. So I go math, prob, you see the factorial button? Actually, I got to put 13 first. 13 math, prob, factorial, and I get a gigantic number, 622,702,0800 over 6 factorial, 6 math, prob, factorial, 720, and then I can divide that number divided by, I take that first number divided by 720, and I get still a very large number, 8648640. In other words, 8 million. Select that playlist. I can also, by the way, do this in the calculator directly. I type 13, go to math prob again. You'll see there's an NPR. Then I've got to put the number after it, the 7, hit that, and I still get 8,648,640. So you actually don't have to use this formula. You can just put this directly in your calculator. Anyway, that's a lot of different playlists you can create. Now, I'm going to go to the next idea. In this case, I said this order of the 7 songs matter. In other words, I've got 13 songs to choose from. If I go 1, 2, 5, 6, 8, 10, and 13, those are my songs. 1, 2, 3, 4, 5, 6, 7 songs. And I say, instead of doing this order, I'm just going to do it in complete reverse order. 13, 10, 8, 6, 5, 2, 1. This is a different playlist than this one. Unless you don't want that to be the case. If you want these to both be the same playlist, in other words, you've got the same 7 songs, what does it matter what the order is? That is called a combination, not a permutation. So repetition is still not allowed. I can't play the same song twice in the 7 songs. So that's the same as a permutation, except in this case the order does not matter. And that's the last idea we're going to do. I'm going to put some more examples down here. But I'm going to start with this one here. If this is the same playlist as this, you are going to have fewer outcomes. So in other words, if the order matters, you will get more outcomes than the order doesn't matter. Just as simple, this shows it right here. If this is, in the case of a permutation, this is the same, this is a different playlist. In the case of a combination, these are the same playlist. They have the same 7 songs. So the number is less. The formula for calculating it, and I'll show you some examples. First of all, you use big C, this is big P, C for combination, and it's still n things taken r at a time, except in this case the order does not matter. So you still have n factorial over n minus r factorial, just like we did before, except now you add in r factorial in the front. Okay, pause that, write that down. Okay, and I'm going to give you some examples. We're going to use the same example you had here, the song example to start with, which is we have 13 songs and 7 slots, except in this case, I am going to make sure, I'm going to say that the order doesn't matter. So permutations, remember, we had of 13 things taken 7 at a time was 8,648,640. Okay, combinations. So now 13, 7, order does not matter. This becomes 13 factorial over 7 factorial, 6 factorial. So 13, 7 is r, and then 13 minus 7 is n minus r. This part right here, 13 factorial over 6 factorial, we know is that number. But again, this you can just do in your calculator. So you can go math. Oh, actually, I got to put 13 first. 13, math, prob. There's an NCR under there. Actually, that didn't work. Math. Okay, combination of 13 things taken 7 at a time is 1,716. Way, way less. And that is the difference between order mattering and order not mattering. You could also, by the way, have done this calculation just by taking that 8 million number I had and dividing it by, I'll write that in, 8,648,640, then dividing it by the number we didn't put in before, which was the 7 factorial. And I'll do that again, just using the factorial button rather than doing the multiplication out. And you get 1716 as well. I mean, it should be the same number. Okay, that's an example of that. Let me give you one more example. I'm going to give the lottery example, because that's the real one. We're going to do the Florida lottery. So the Florida lottery apparently has 6 numbers, just what I described, from 1 through 53. I think I used 52 last time, is the numbers you can choose from. And as I said, in the lottery, the actual order doesn't matter. In other words, I pick say 6 digits out, 1, 2, 3, 4, and 5, and 6. If they come out of the machine 1, 2, 3, 4, 5, 6, or they come out of the machine 6, 5, 4, 3, 2, 1, you still win the lottery if that comes up as a number. So what does that mean you have? The order does not matter. Also, repetition is not allowed. There's no such lottery number as 50, 50, 50, 50, 50, 50. So it is a combination of 53 things taken 6 at a time for 6 numbers. So that is 53 factorial over 6 factorial, 47 factorial. And I'm just going to do this one out since it's the last problem. Do it by hand. 48 times 47 factorial. So go down to 47 factorial, so I can cancel that. And I still have 6 factorial, unfortunately, over here. There we go. So the answer is the total number of lottery numbers is 53 times 52 times 51 times 50 times 49 times 48 divided by 6 times 5 times 4 times 3 times 2 times 1, or 22,957, 480. That's the total number of lottery numbers. And what are the odds of you winning a lottery if you buy one ticket? 1 over the total number of outcomes. In other words, not a fat chance. There's your odds of winning the lottery, of buying one ticket. And roughly the Colorado lottery is about the same as that. Okay, so that's the total, that's all about counting. And let me just review this first and I'll give you the homework. We reviewed the fundamental counting principle, which just basically says multiply numbers together of each individual event, and that gives you the total number of events. So multiply individual outcomes to get the total number of outcomes. And repetition is allowed for fundamental counting principle. Permutation, repetition is not allowed. And we give a number of examples of that. Also, the order is important for this. This number is always bigger than this number. Combination, repetition is not allowed. Again, just like the permutation, but the order does not matter, and therefore this is much less than that. All of these are actually ideas of getting, remember, the denominator, the total number of outcomes. We'll talk about next time about the numerator of the probability function. Okay, so homework. We're going to do homework number 20, which is called Counting Principles. All right, until next time, thanks.